Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is the combined Rankine-Brayton cycle, and the section in the textbook is 10.9. So here are the 4 learning outcomes for this video. At the end, you'll understand some of the benefits of combining a Brayton and Rankine cycle together. You'll know the basic components of this combined cycle. You'll be able to draw the TS diagram for the combined cycle, and finally you'll be able to solve for the conditions of the thermal efficiency of the combined cycle. So first, let's kind of answer the question, why a combined cycle? So let's go back and look at a Brayton cycle. So that's what we have on the diagram over here, where we have the compressor on the left and the turbine on the right, and a combustor with heat input up here where we have Q in. And one of the things about the Brayton cycle is we draw it on a TS diagram. Here I'm looking at an isentropic compressor and turbine, just to focus on the combined cycle here, is these can operate at really high temperatures, at temperatures greater than, say, 1,000 degrees Celsius. And it's really just limited by the components of the turbine. And what that means is that these outlet temperatures, as I've shown over here, can still be really warm. And even if you're using a regenerator, you're still losing a lot of energy between this dashed line here. And so it sure would be nice if we could go ahead and recoup some of that energy. Well, we can get an idea of how to do it if we were to superimpose the water phase diagram on this TS diagram. So let me note that this blue line, okay, is for air, okay, and the blue line, or sorry, the dark blue line is for water, but the temperature scales are the same. And so the saturation curve for the gas, the light one, would look way down here. This is way out in ideal gas land. But what you notice is that this outlet temperature is actually well within the saturation curve, and maybe we could go ahead and boil water with that. And that's exactly what the combined cycle does. So instead of exhausting that hot gas, what we do is we run it through a heat exchanger. This heat exchanger replaces the boiler of the typical Rankine cycle. So if you look on the bottom here, we've got our traditional Rankine cycle with a pump. We replace the boiler with this countercurrent heat exchanger. So we're taking the warm air that we would normally exhaust from the Brayton cycle, and we're boiling water with it, and then running that through a Rankine cycle. And then we're going to go ahead, and down here is my Q out. And this is at a very much lower temperature than our combustor up here, and definitely much lower than the temperature of the exhaust of just the Brayton cycle alone. That means we're operating a cycle between a larger temperature difference, and we can end up with a much higher efficiency. So here, if we kind of look at what the Rankine cycle would look like on here, I've drawn this up in green, is that we're now taking heat from there to go ahead and heat and boil this water. And so it's sort of like a regenerator, but we're actually adding it to the Rankine cycle. And what we're going to see when we do an example is this is even a higher efficiency than if we were to use just a regenerator in the Brayton cycle. Okay. Well, there's one thing we're going to do before we can solve the problem, is that when these two things are combined together, is that this heat exchanger that's operating between the air and the water, so the air is the upper fluid and the water is on the bottom, is that the amount of energy being extracted from the air balances the amount of energy going into the water. And that's actually going to determine the relative mass flow rates in the two cycles. So if we were to go ahead and write that energy balance, we would have the mass flow rate of air and its enthalpy change, which is going to be using the notation out here, H8 minus H9. This is the hot air coming in on this side. And that's going to be balanced with the mass flow rate of water times H3 minus H2, all right, for the water. And what this does is this fixes what the mass flow rate of water is relative to the mass flow rate of air, such that this heat exchanger energy is balanced. So we've got energy going from the air into the water. So that's the last energy balance that we're going to need to go ahead and solve problems using the combined cycle. So here's the example we're going to do. And so I've again just shown the diagram here for a combined cycle where our heat input up here. And what a couple of the specified numbers is, our combustor is going to be operating at 1200 degrees Celsius and 700 kPa. And so if we assume air is coming in at atmospheric, this is a pressure ratio of 7, so RP is equal to 7. And we're going to be operating our Rankine cycle, our water Rankine cycle, with a condenser down here at 30 kPa. We're going to also specify the mass flow rate of air at 25 kilograms per second. So that's the mass flow rate of air going into the Brayton cycle. And then one other thing we're going to specify is that the outlet from the Brayton cycle over here, the outlet after that heat exchanger, is going to be 200 degrees Celsius. And so what that is that's this 0.9 right over here. So I'm specifying that at 200 degrees. And so we need to make sure that that is at least warm enough that it can begin to boil the water. And so clearly, as long as it's much above there, we're going to be able to boil that temperature. We're going to make one other assumption, is that we're going to assume that the temperatures at 8 and 3 are equal to the same. So we have a really, really efficient heat exchange. It'll just make the analysis a little bit easier. All right. So what I'm going to do is go ahead and solve this problem in EES. So here I've got this problem set up in EES, and I'm going to move through the Brayton cycle a little quicker than we have in the past, because I think you've seen plenty of these now. But let me just review. The top 4 lines that I have are my specifications of what was given in the problem. So I've got an input pressure and an input temperature of room pressure and room temperature, pressure ratio of 7, and the combustor at 1200 degrees. And then, as we've done before, we have our isentropic compressor. So we're specifying the pressure, high pressure, just wrote the pressure ratio. Then we've got our 3 steps for isentropic, and we'll do the same thing for the turbine. So let's just make sure that this gives us a solution. So here we go, and there's our array table, and we have all of our pressures and entropies. So we should be able to keep moving through. So we can go ahead and uncomment the next line, so we'll find out what the efficiency of this Brayton cycle is. So if we look now at what I have, is I've just found my enthalpy using the temperatures of the air, and then my efficiency. And so the heat input is 7 to 6, and the heat output is 8 to 5. Ignore those commented lines. I'll mention those in just a moment. And then my efficiency of the Brayton cycle, 1 minus Q out over Q in. So now if we look at when we solve this, our efficiency is 40%. This is without a regenerator. So let's look at what our efficiency would do if we were to go ahead and add a regenerator. So let me remind you, if we have a regenerator, and in fact, if we had a perfect regenerator, so if we look at our diagram over here, if we had a perfect regenerator, we would be able to combine those points right there. And so our heat output would actually be down here. So it was going to be between the temperatures of T6 and right over here, which is the input, which is T5. And then the heat input is actually going to become only at T8. So it's going to come in right there. So there's going to be a substitution. Instead of T6 for heat input, I'm going to use T8. And instead of, I'm going to be using T9 instead of T8 for that as well. So if I return over here to EES, that's what these 2 lines do over here. So let me go ahead and change this. So this is going to effectively just change it and make sure that I have a perfect regenerator. So this is going to be the best that I could do. All right. So now if I look at where my efficiency, I've gone from 40% up to 66%. So the regenerator definitely increased the efficiency a lot. We're up at 66%. But what I'm going to go ahead and do now is let's find out what happens if we add a Rankine cycle on the bottom of the cycle as well. So, all right. So first I'm going to go ahead and remove that regenerator. So I'm going to go ahead and remove those comments that I did and go back to what we had originally. And that way we're effectively calculating the correct Q in and Q out of the Brayton cycle. And now let's go ahead and look at our Rankine cycle. And so again, I'm going to kind of move through this a little bit quicker. But let's look at what we have. T3 equals T8. Remember, that's what I said, was that I'm assuming that the output of the turbine from the Brayton cycle is going to be the highest temperature in the Rankine cycle. So it's sort of an assumption. There's my compressor, or my condenser pressure, and I'm saying that this is operating at 3000 kPa as well in the Rankine cycle. And then, of course, the outlet of my condenser is a saturated liquid. We have some isobaric steps. I'm assuming an isentropic pump and turbine again. And so if we go ahead and look at our solution table, we realize that here's all of our pressures and entropies at all of the points. So our problem is completely specified both for air and for water. So now we can go ahead and calculate our enthalpy values. At all states. So now I have enthalpy values of all my air and of my water. So we're getting close to being done. But there's one thing that's left, and we've got to go ahead and balance the mass flow rates to go ahead and do the energy balance over the heat exchanger. So there's going to be my last step. So let's go ahead and look at that equation here that I have. All right. So if I go down here and look at my heat exchanger equation, there's what we had on that previous slide, where I'm balancing the mass flow rate of air and its enthalpy change, the mass flow rate of water. It was specified that the mass flow rate of air was 25, and then I said that the enthalpy at H9 was 200 degrees. So now we can go ahead and find our combined cycle efficiency. Right? So looking up a couple lines there, I see Q out from the Rankine cycle is 4 minus 1, right? And that's all per mass. So now my efficiency, let me just go back once to the diagram of ours. So we have one heat input, and that's Q in from the Brayton cycle, and we have one heat output, and we have Q out from the Rankine cycle. So in terms of this combined system, this is Q in and this is Q out. So if you look at my efficiency equation here, I have 1 minus heat out, and I'm multiplying by the mass flow rate of water, so this is an extensive value, and the mass flow rate of air. So if we go ahead and look at what our solution is now, this is the efficiency of the combined cycle, and now we're at 71%. So when we used the regenerator, we got up to 66, but by adding this Rankine cycle, we were able to tweak out another 5% in terms of thermal efficiency. So that's why the combined cycle is yet even more efficient than a Brayton cycle with a regenerator.